In this example, we'd like to show that this function right here is a probability density function. So in general, we need to show that this function is, number one, continuous. Because it's defined by an exponential, that's taken care of for us. We don't have to worry about that. Number two, by the way, this is a probability density function on the entire plane, R2, so the region D is the entire plane. We need to show that this is positive, again, because it's defined by an exponential. E to any power is non-negative. So it's not only, we're supposed to show it's non-negative. I wrote positive. It is positive, so therefore it's non-negative. And then step three is to be a probability density function, this function must obey this property, that the double integral over R2, the entire plane, e to the minus x squared minus y squared times 1 over pi dA, this integral should equal 1. And so that's the work that we have to do on this one. But before we get to that integral, this distribution is very important. It's called normal distribution. And this one looks like, and let's just try to sketch the surface of this. So in the zy plane, if you just zero out x, then this looks like e to the minus y squared times 1 over pi. And so this curve looks like a Gaussian bell curve that we've all seen in this direction. And if you do the same thing, you zero out the y and you think of the x, it also has the same shape in the x direction. It looks a little bit different as you try to sketch it. And as you then spin this around, you end up with a surface that traces out bell curves in every direction. And so it has like a little hump in the middle, and as you go out in any direction, this thing flattens out and approaches the plane. Okay? And so you can kind of picture a bell curve that's been spun around the z-axis and creates a little bump near the z-axis, and then spreads out nicely and smoothly in all directions from there. Okay, but it's good to visualize, but what we really want to do is compute this integral. So let's get some clean paper and look at this integral, but the way that I've drawn this actually gives us a hint as to how we're going to compute this integral, and so we'll look at that on the next page. Remember, the integral that we want to compute is the double integral over the entire plane of 1 over pi. That 1 over pi can be factored out because it's a constant. And what we need to integrate is this, e to the minus x squared minus y squared dA. And this is, of course, going to be an improper integral because we have to integrate over the entire plane. So let's write this out in Cartesian coordinates and see what it would look like. Number one, to fill out the entire plane with little rectangles, those little rectangles need to extend from negative infinity to infinity in both directions, the x and the y. E to the minus x squared minus y squared. This could be dy dx or dx dy. It doesn't matter. This is very symmetric. And then we could use the properties of the exponential to break this up into two integrals. So 1 over pi, integral minus infinity to infinity, e to the minus x squared dx times e to the integral negative infinity to infinity, e to the minus y squared dy. This is separable, and in some ways this might look better, except this integral we've seen before. There's no simple function antiderivative of e to the minus x squared, so we actually don't know how to compute this other than to do an approximate integration, Riemann sum type argument, and to get we want to know the exact answer here, right? We want to show that this whole thing becomes 1, so this is maybe not the best way to do this. So we need another way, and what we can do is we can go back and look at this original integral and notice that this looks like just minus parentheses x squared plus y squared. And if we go back to our picture of the region, notice I drew these concentric disks or circles that kind of trace out the same height around this surface. And so this gives us an idea. Let's try using polar coordinates. Alright, so polar coordinates are our friend when they work, of course, definitely when they work, but they're always our friend. Alright, so number one, in polar coordinates, this exponent becomes simply e to the minus r squared. At first glance, that's not going to fix anything, right? But then we can remember what happens to dA in polar coordinates. The area element for a polar rectangle is r, dr, d theta, and now that r and this r squared are going to work together and help us actually compute this thing. So let's think about how we can fill out the entire plane in polar coordinates. So let's just think we've got our x and our y coordinates. We start at the pole, and the first thing we do is r traces out some distance in the positive x-axis, in the direction of the positive x-axis, and then to fill out a disk of radius r, theta just zips around, and theta goes from 0 to 2 pi. Okay, so no matter what our r is, we're going to trace out these little disks from 0 to 2 pi, and then we can expand these disks by letting r go to infinity. So r is going to go from 0 to infinity in the polar sense. So notice up here we had improper integrals in really 4 senses. We have a negative infinity and an infinity for each variable, and in polar coordinates, to fill out our entire plane, our integral, so this is the integral we want to compute, 1 over pi, double integral over the entire plane, e to the minus x squared minus y squared dA. To trace out this entire plane, or fill out this entire plane in polar coordinates, we need to go integral from 0 to 2 pi for the theta direction. That is not an improper integral. That's totally fine. And then integral from 0 to infinity in the r direction, that's only improper as we go to infinity. We've already talked about how to switch the coordinates here. Our integrand becomes e to the minus r squared. No thetas there. And then our dA has to become r dr d theta. And this whole thing can be broken up now into 1 over pi. It's separable. The theta integral is just 0 to 2 pi of 1 d theta. And then this integral is improper, the r integral. But that improper integral, so let's treat it properly. This has to be converted to the integral, the limit as t approaches infinity of the integral from 0 to t of r e to the minus r squared dr. And of course we're going to make a u sub here and just let u equal r squared. So du should equal 2r dr, which means we need a 2 here and a 1/2 out here. Okay. But as we make this change, we can just keep the 0 and the t the same, because as r goes to infinity, u also will go to infinity here. So we don't need to worry too much about that. But now we just compute. So this integral, the 1 over 2 pi can hang out in front. There's a 2, this 2 right here comes out here. This integral is just another factor of 2 pi. So those are going to cancel. And then the antiderivative here, this becomes e to the minus u du. So this becomes then, the antiderivative is minus e to the minus u, evaluated from 0 to t. So again, this just becomes 1. When we plug in, we get e to the 0, negative e to the 0. So this becomes 1 minus e to the minus t. And then we take the limit as t approaches infinity. As t gets really big, e to the minus t gets really small, and this limit, of course, equals 1. And so that shows us that our double integral of our probability density function, which we didn't know was a probability density function until we finished this integral, but the double integral of this function over the entire plane is 1, and so therefore this is a probability density function. Okay, so we can check this off. That's done. And again, this is called the normal distribution. So this probability density function is very important in statistics and other areas.